Hello my dear students and welcome to this lecture series by AKTU. I am Dr. Supriya Frailatpam, Assistant Professor in Babu Banarsi Das Institute of Technology and Management. I will be taking Environmental Engineering KCE 603 for you. Today is my fourth lecture for Unit 5. So, in fourth lecture I will be we will be talking a little bit on the trickling filter and then we will continue that with contact beds and rotating biological contactors. Okay. So, let me so what we have done here is that, so we have done this part, we have done this part, we have finished a little bit of this. So, today we will be talking about here this and contact beds. This already we have to discuss. We have talked here. Today we will be talking this and this, right? And the next classes we will be talking about this part and this part. So, in my last lecture we have talked about trickling filters. So, today what we are going to see is for solving problems on trickling filter, you should know the efficiency of a trickling filter. So, you should know some formulas which will be required for solving of problems for trickling filters. So, for trickling filters we have efficiency of a trickling filter. This efficiency is very required. This formulas, they are called NRC. Okay. So, NRC equations. So, for efficiency of a conventional trickling filter is eta in percentage equal to 100 divided by 1 plus 0.004 to the root u. Okay. This is for a conventional trickling filter, and for a single stress trickling filter we have this, okay, here. So, in this single stage filter we have this F. So, what is this F? This F is called the recirculation factor. So, recirculation factor in the sense, so this is recirculation factor. So, what is recirculation factor? F equal to 1 plus R by I and 1 plus 0.1 R by I whole square, right. So, you have to remember this formula and this formula. Okay. So, here what you have is that, what is Y here? Y here is the total organic load in kg per day applied to the filter, that is the total BOD in gram in kg, right. V is the filter volume in hectometers, right. This U is organic loading in kg hectometer per day applied to the filter. So, U is can also be here, U is equal to Y by V F. F is the recirculation factor, and what is R by I? Which is, you can this one R by I, this is the volume of sewage recirculated, R to the volume of raw sewage, right. So, before I talk a little bit, let me just come back to you. So, what we have talked in my last lecture was that we have talked about conventional or trickling filter and a high rate trickling filter, right. What was the difference between a conventional and a conventional and a low rate trickling filter and a high rate trickling filter was the term recirculation, right. So, in a low rate trickling filter we used to have the primary sedimentation tank and then the trickling filter and then the secondary sedimentation tank, right. This is low rate, right. So, in this case you use this formula, right. Okay. In the next case, in terms of high rate trickling filter, we have a primary sedimentation tank followed by a trickling filter or a series of trickling filter, whatever you want, right, and a secondary sedimentation tank. This is a single stage trickling filter. What is the difference between this low rate and high rate is that we have a recirculation factor here R, right. So, what does it means that if in this we have a factor called R. So, here what is the R? R is the volume of sea waste recirculated. So, a percentage, so R may be 10%, 20%, whatever you want. A percent of the effluent which is coming from the trickling filter is sent back to the trickling filter, to the inlet of a trickling filter again, and again it is gone through, right. So, this is to the volume of the raw sea waste. So, here if R is 10%, what will this factor be? 10 divided by volume, 10% by 100, right. So, it is going to be 0.1, right. So, this here. If we do not have any recirculation here, this what is this F going to be? If there is no recirculation, that is if R is 0, okay, no recirculation, so R is 0. What is R 0 then? F equal to 1, right. In this case, U equal to Y by V, right, and then this U by V. So, Y by V, and now this equation changes back to here, right. So, this is the main equation. So, if for single stage or for high rate trickling filter, you are going to have recirculation, and for low rate trickling filter you are not going to have recirculation. So, remember this always, when you talked about a difference between high rate and low rate is just the recirculation. When you sending back a part of the effluent from the trickling filter to the inlet of a trickling filter, again you are recirculating, right. So, that is makes a high rate. So, this is the formula, you have to remember this, it is a very easy equation, right. Now, let us talk about what are the advantages and disadvantages of trickling filters. So, trickling filter, very lots of advantages, at the same time some disadvantages. What are they? So, advantages is that they are simple, reliable biological processes with low power requirement. So, you do not require more power, you just require power for pumping of the effluent, right, from the sedimentation tank and sprinkling it over the trickling filter, right. So, you do not. So, for example, when we talked about activated sludge process, which we will be talking in the next class, we are talking about huge amount of power consumption, but here very less amount of power consumption, right, because whatever oxidation is taking place, it is taking place like naturally. And then it is suitable in areas where large tracts of area are not available for land intensive treatment. So, it is suitable for areas where we have area like it requires a part of area requirement is there, lesser than activated sludge process area requirement, but more than others. It has more land requirement than activated sludge, but it has lesser land area requirement than lots of other treatment systems, right. Then may qualify for equivalent secondary discharge standards. The trickling filter, the effluent of a trickling filter from most of the time low rate trickling filters, they are very good and they can be discharged directly to a river also. They have got very good discharge standards. Effective in treating high concentration of organic depending on the type of media, appropriate for small to medium sized communities, right. For small towns or maybe small cities also with comparatively lesser population, we may go for trickling filters, but for large cities we generally go for activated sludge or other more advanced treatment like UASB or something like that. Most of the time we go for activated sludge at this time at this point of time, right. But trickling filters can go for medium sized or small sized cities or towns, right. Rapidly reduces soluble BOD in applied wastewater and efficient nitrifying qualities. Okay. Moderate level of skill and technical expertise uses to manage and operate systems. So, you do not require many skilled people, you can easily manage with the local staff there. Works efficiently in warm weather like those prevailing in India. Okay. So, this is a very important term. So, you know what, the treatment system in European countries where it is very cold is going to be extremely different from what we have in a hot place like India. So, India, by God's grace, we have a very good environment very conducive for treatment. So, we do not generally worry about frozen water pipes, we do not generally worrying about this biological treatment systems, the bacteria in the biological systems dying, because we live in a very warm, nice place, right, in which the bacteria they flourish. You do not have to do anything more, right. But in places where in cold places, imagine those filtering medias will be there, if that it is left in the open and the trickling filters are there. So, it may get very cold on those, and those filtering medias may get frozen so frozen in the sense those bacteria will die. So, trickling filter is not going to work in those cases, right, or if you want to work, you may have to heat up the whole environment, right. So, what are disadvantages? Disadvantages are they cannot treat raw sewage, high head loss, right, higher cost of construction. So, initial construction cost is going to be less, but the operative cost is going to be comparatively lesser. Requires regular operator attention. Incidence of clogging is relatively high, though the filter medias may clog very soon. Requires low loading depending on the media. Flexibility and control are limited in comparison with activated sludge process. Activated sludge process are very in process right now. Vector and order problems may be there, and ponding problems may be there. Vector problems and order problems means that you have wastewater which is like literally outside. Okay. So, you may have lots of mosquitoes, you may have lots of flies, it may smell bad, right. So, people who are staying near that, they may not like trickling filters. So, these issues may crop up, right. Then, so these are the issues. Now, let us come to a question. So, this is a problem for trickling filters. So, what is the question here? The sewage is flowing at 4.5 million liters per day from a primary clarifier to a standard rate trickling filter. So, standard rate in the sense low rate trickling filter. The 5-day BOD of the influent is 160 milligram per liter. The value of adopted organic loading is to be 160 grams per meter cube per day, surface loading of 2000 liters per meter per day. Determine the volume of the filter and its depth, also calculate the efficiency of the filter unit. Okay. So, how are we going to solve this problem? So, what is given? Total 5-day BOD is 160 milligram per day. So, we are going to calculate this BOD for per liter 160 milligram. So, for 4.5 million liters, how much? 160 into 4.5 million, right. This is in milligram, this grams per day. So, this much of BOD is present, right. Then volume of filter media required will be how much? Total BOD by the organic loading. So, what is the organic loading here? Here, okay. So, here what you are going to see, if you get confused, just check out the units. Okay. Here it is gram per day, right. What you require is volume. So, it is going to be meter cube, right, and total BOD is you are giving in grams per day, right. Here this is the surface loading is what? The organic loading is 160 grams per meter cube per day. So, if you divide this gram per day by this gram per meter cube per day, you are going to get meter cube, right. So, this is another way of if you get confused, you have to think like that. So, volume of the filter media required is total BOD by organic loading, that is 72000 720,000 by the 160 grams per meter cube per day, which gives a volume of 4500 meter cube. So, what you require, the answer is here, this answer is this. Okay. Now, once you have the volume, you can easily calculate the surface area, right. So, surface area required for the filter is total flow by the hydraulic loading, how much you are loading, hydraulic the surface loading. Okay. So, total flow is 4.5 million liters, right, divide by the surface loading or the hydraulic loading, which is 2000 liters per meter square per day, right. So, here again million liters and here liters per day. So, you get meter cube meter square. So, total flow by hydraulic loading 4.5 into 10 to the power 6 divided by 2000, you get 2250 meter square, right. So, this is the surface area. So, you have the volume, you have the surface area, you can get the depth, right. So, depth of the bed required will be 4500 volume divided by the area. So, depth will be volume by area, right, 4500 by 2250. So, you have 2 meters. Now, efficiency of the filter. So, what is the efficiency of the filter here? The efficiency of the filter as given by NRC equation was 100 divided by 1 plus 0.0044 root over u, which where u was the organic loading in kg. Here what you have to remember is, you have to remember this kg per hectare meter per day, right. So, whatever is given in is not given in hectare meter per day, you have to convert that into hectare meter per day. So, what is the organic loading here given here? Organic loading was 160 grams, sorry 160 grams per meter square per day, right. So, meters, this then you have to convert to kg per hectare meter per day, right. So, you just require this value. So, u equal to organic loading in kg hectare meter per day, which is 160 by 1000. So, 160 grams converted into divide by 1000, this will give in kg, right, and then meters cube 10 to the power 4, if you multiply you will get convert that into hectare meter, right, per day. So, put this value here, you get eta equal to 85.03%, right. So, by using this equation you can easily calculate your efficiency of the trickling filter. Now, let us come quickly to the next aerobic attached culture system called contact beds. Okay. So, this is actually the most important aerobic attached culture is trickling filter. So, you should go in depth for trickling filter. Contact beds are important, but not that important. The second most important aerobic attached culture system will be RBCs or rotating biological contactors, which we will be talking about. Okay. So, let us quickly go through this contact beds. So, they are also known as contact filters or contact beds. So, it is actually very simple, it is similar to a trickling filter, but here you generally do not trickle. Like in trickling filter, what is happening? You are trickling the wastewater, right. In this you do not trickle, you simply collect the wastewater, keep it in the filtering media and then just let it go, keep that filter media empty for a period of time and then again you put a new influent. Okay. So, it is like that. So, what is in contact filters, what you do? You put the influent, keep it for a particular time, take out the influent, keep the filter empty for a long period of time, longer period of time and then again what do you do? Again you put it, you start the first process again. So, in this system COS is kept in contact with the filtering media for a certain period of time, around 2 hours. This is the first contact period. So, why contact beds? In contact beds, what you have to remember? You have contact periods here. Okay. That also 2 contact periods, 1 and 2. In the first contact period, you keep it for 2 hours, remember it. Okay. In this system, COS is kept in contact with the filtering media for a certain period, around 2 hours, first contact, which leads to formation of a film of organic matter around the filtering media. Same as trickling filter, the filtering media is there, you will keep it for 2 months, what will happen? Those media will be building on the filtering media, right. then the filter is left empty for a certain period, then you let the water go. Okay. The filter is left empty for a certain period around 4 to 6 hours, second contact period. So, this is 4 to 6 hours. So, in contact beds you have two types of contact period, during which the filter will absorb oxygen from the atmosphere. So, it will build, and then once the water is gone, what will happen? Oxygen will come on this and they will have ample oxygen. So, those aerobic decomposition is going to take place. Aerobic bacteria present in the sewage will oxidize this organic matter through aerobic decomposition, right. The stabilized organic matter from the first cycle will be washed away by the fresh sewage in the next cycle of operation, right. It will keep on building, now full fine. Afterwards, when the next cycle takes place, water is going to come and this is going to, it is going to take it out. So, the slogging is going to take place, right. So, the process keeps on repeating. So, first contact period and then the second contact period. So, what is happening here? From the primary sedimentation tank, you have water here, and then the filtering media, water is kept here, then around. Okay. So, here dosing media, right, water will be the influent will come, the effluent from the primary treatment is going to come out here, right. These are contact beds. Then, so what is the problem here? The problem here is what is the problem here? Contact beds are operated intermittently and hence several units would be constructed. So, what is happening? You are having two contact periods, one contact period and then the second contact period, right. So, what is the problem now? But the sewage is going to keep on coming. So, when the one contact bed is in use, you need other contact bed to be in use. So, you should have a series of contact beds, right. So, contact beds are operated intermittently and hence several units should be constructed. It removes around 80% of the suspended solids and 60 to 75% of BOD. Rate of loading is very low, around 110 liter per meter per day per meter square for depth of 1.2 to 2 meter. For every 4 to 5 years, the filter bed should be removed, washed and dried as it gets fully clogged. The under drains are also washed and the beds reinstated. They are not used nowadays due to poor loading, which leads to requirement of large areas, right. Now, so now let us come very fast to the next topic, which is called aerobic attached culture or culture system, that is rotating biological contactors, right. So, RBCs. So, this is what an RBC looks like. So, what is this? So, what I was telling you about attached here, these are the films, okay, and those bacteria are going to get attached to these films. So, before it was filtering media, now you have a filtering, you have a layer, okay. So, in RBC, media in the form of large flat disc are mounted on common shaft, right. This is a common shaft here, which is rotated through specially contoured tanks in which wastewater flows on continuous basis, right. The discs are submerged into wastewater about 40% of a diameter. So, around here they will be submerged, right, and rotated by power supply to the shaft. So, this will keep on rotating. So, what will happen? This will go on rotating like this. The shaft, it will rotate. So, once you have this, so once you have the wastewater, it is under the wastewater, and then when it moves, it comes on the in atmosphere. So, what will happen? It will take up oxygen from the atmosphere and it will turn again. So, once take up the wastewater, aerobic space, and then again go inside, right. Approximately 95% of the surface area is alternately immersed in wastewater and then exposed to the atmosphere above the liquid. So, you get oxygen from the atmosphere, right. So, the medium consists of plastic sheets ranging from 2 to 4 meter in diameter, right. They are plastic sheets, right, here sheets, and a diameter and up to 10 thick. So, 2 to 4 meter diameter and 10 thick. spacing between flat discs is approximately 30 to 40 millimeter and mounted on steel shaft up to width of 8 meters, right. The shafts have around, they are around 8 meters. The shafts are rotated at a speed of around 1 to 2 rpm, very slowly, okay, 1 to 2 revolutions per minute, slowly, which is sufficient to provide hydraulic shear necessary for slogging and to maintain enough turbulence to keep the solids in suspension as the wastewater passes through the tank. So, slowly it is going to move, take oxygen, go inside, come back, take oxygen, go inside, right. So, microorganisms growing on the media on the medium surface removes food from the wastewater and oxygen from the air to sustain their metabolic process. So, in the when it comes to the atmosphere they take oxygen, and when you go to the wastewater they get food. So, you getting both food and oxygen, right, one's food and another oxygen. Thickness of the biofilm varies up to 2 to 4 mm depending on the wastewater strength and rotational speed of the disc. Advantages include stable dense sludge which settles well in secondary clarifier, low power requirement and simple operating procedures, right. Disadvantages include high capital cost and sensitivity to temperatures. So, sensitivity to temperatures. Okay. So, for all biological systems temperature is going to be a problem, right. So, thanks a lot. With this we have finished aerobic attached systems. Next, in the next class we will be talking about aerobic suspended systems. Thank you class.